Hi everybody. Today we're going to have a quick look at two-step experiments. But before we do that, let's have a look at a single-step experiment. So a single-step experiment typically is a list that's used to display a sample space. So in the case of a coin toss, that would be heads and tails. In the case of a dice, that might be 1, 2, 3, 4, 5, 6. But sometimes we want to do more than one step in an experiment. So if we're doing two coin tosses, or two dice, or two of anything really, we can use a table, and that will help us find the sample space. So in this case I've got two coins tossed, and in the columns I've put the first coin, and in the rows I've put the second coin. Doesn't really matter which is which, as long as they're different and you list them in the same order all the way through the sample space. So if I tossed a head and I got a head the second time, I would get head, head, head the first time, tail the second time, head, tail, tail the first time, head the second time, tail, head, tail the first time, tail the second time, I'd get tail, tail. And I could summarize that in a list if I wanted to, like this. Similarly, I could do it for a bag with a red, green and blue counter, where I take a counter out, look at it, put it back in the bag, and randomly choose a second counter. So if I look at the first one, it's not going to work. If I could pick a red out the first time and a red the second time after putting the counter back in the bag, I would get red, red. Similarly, red, green, blue, green, red, green, 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 blue, blue, red, blue, green, blue, blue. There are 9 possible outcomes. They're all equally likely. Given that they're equally likely, I could find the probability of red, red, which would be this first case over here, would be 1 over 9. If I wanted the probability of 1 red, that might be this one, this one, this one, this one. Only one would be 4 out of the 9, and both the same color. That would be this diagonal, red, red, green, green, blue, blue. That would be 3 out of 9, or a third. Okay. But what if we don't put the counter back in the bag? In this case, this is without replacement. That's what we call it. If we take a red out the first time, we won't have a red to pick the second time. There's no way to get this outcome. I'll put a dot here. If we get a green the first time, we can't get a green the second time, put a dot there. Same for blue. It's restricted. It's reduced our sample set size. So instead of having 9 outcomes, we've now only got 6. And I've listed that over here. So the probability of picking red, red now is impossible, because we didn't put it back in the bag. Of only 1 red, we'd have 1, 2, 3, 4 out of our possible 6. And both the same color we can't get anymore, so that would be 0. So whether replacement occurs or not is really important, and we're looking for clues in the question to tell us whether replacement's happening. So here's an example. We have tiles of the word banana being placed in a bag. 2 letters are taken out and placed on the table. So if they're taken out and not put back, then this is without replacement. So our diagonal, if we get a B, we can't get a B on the second tile. So, and the same with A and blah, blah, blah. So I'll put a dot through the diagonal. And the first question is, how many different 2-letter arrangements are possible? Well, if it starts with A, we've got AA, AB, and AN. If it starts with B, we've got BA and BN. We can't make BB, because we've only got one B. And if we have starts with N, we'll have NA, NB, and NN. So there's a total of 8 different arrangements. If we're looking for the cases where there's at least one A, so at least one A indicates it'll be 1 or more A's. And I have highlighted here all the outcomes that have at least one A. There's 24 of them out of the 30 possible outcomes. So that's what I've written here, and simplified that down to 4/5. If we're finding the probability of 1B given at least 1A, the denominator is going to be the 24 we found out earlier. And of those that have at least 1B, I've circled in green up here, there's 6 of those, which would give us a total of 1/4. And that's a very simple introduction to two-step experiments. They get a lot more complicated than these cases, but it's a nice starting point. So I hope that helped, and I'll speak to you soon. Thank you very much.